There's another context in which Bernoulli trials, independent Bernoulli trials, arise somewhat naturally. It is the idea of counting the number of trials required before the first success occurs or before the first failure occurs. So that's going to be the random variable with which we'll work here. We call this the geometric random variable, and it has a probability mass function, assuming that the probability of success is p, probability mass function given by this expression. 1 minus p, the probability of failure at every step, times x minus 1 times p, the probability of success. So what this is saying here is that you have basically failed x minus 1 times, and then on the xth attempt you succeed. So what's the probability that it takes you x attempts? Well, x minus 1 failures to start with, and then eventually 1 success. Here, unlike what we had for the binomial distribution, you can expect that the number of attempts could, in theory, be infinite. You can imagine, if there's a probability, say, that is not equal to 1 of success, that you will never be successful. In theory, you could take a coin, and you could flip it, flip it, flip it, flip it, and never get heads, even though it's a fair two-sided coin. When we're talking about a geometric random variable, we write it as geo with parameter value p. So we'll say that x follows a geometric random distribution with parameter p, and we write it geo p. For this specific random variable, you can show that the expectation of the number of trials would be 1 over p. Think of this makes sense. Think back to the coin, which has a probability 0.5 of being successful, say flipping heads. Well, in theory, you would expect to have to flip it twice on average in order to be able to observe your first heads. The variance, 1 minus p divided by p squared. These are specific values that you should remember or know. As an example, let's say you throw a fair 6-sided die until it shows a 6. So that's going to be the success, showing a 6. What's the probability that you need 5 throws? Well, you're trying to compute the probability that x equals 5. And here x follows a geometric distribution, geo 1 over 6. The probability of rolling a 6 is 1 over 6. In that case, if you just plug in the values, p equals 1 over 6, x equals 5 into the formula for the PMF, you will get that the probability that it takes exactly 5 throws before you roll a 6 is about 8%. Now, how many throws would you expect to need on average? Well, on average you would need 6 throws. 1 over p, 1 over 1 over 6, which is itself 6. This is aligned with what our intuition tells us.